Let's first see formation of oxides by alkali metals. Very first element is lithium oxide, L2O. Now this oxide we see two lithium atoms and one oxygen atom with two negative charge, O2 having a very high electron cloud density with two extra electrons over a very small sized single oxygen atom. This high electron charge density is stabilized by lithium ion because of its small size and high polarizing power. So what we see is a distortion in the O2 negative atom by two strongly polarizing lithium ions that stabilizes this negative charge on oxygen atom, making a stable oxide L2O. Now we will see N2O2 or sodium peroxide. We know sodium ion having a relatively large size than lithium. So O2 negative having electron cloud density spread over two oxygen atoms. What was distributed over a single atom of oxygen in case of a L2O, in N2O2 or sodium peroxide, the same charge is distributed over two oxygen atoms. So relatively, this electron cloud density is lower in case of peroxide. That's why it is easier to stabilize this large-sized O2 two negatively charged anion by two large-sized sodium ions. Thus, Na2O2 is stable structure because of large size of sodium ion that can stabilize large-sized O2 negative peroxide anion. And what we see, we are talking about potassium superoxide, rubidium superoxide, and cesium superoxides. In these superoxides, a single unit of negative charge is distributed over two oxygen atoms. So electron cloud density is relatively small over these oxygen atoms. Thus, there is not a big electron cloud density for distortion. On the other hand, the counterpart cation, potassium, rubidium or cesium, having a relatively large size that can be stabilized with these superoxides. So this dispersed electron clouds are stabilized by large-sized cations. So from that you can understand smaller size cations can better stabilize the high electron densities, while low electron densities or distributed electron densities are better stabilized by the larger cations, bigger size anions, bigger size cations, and having low electron density over anion. That is the reason for the stability of superoxides. For the same reason, these large-sized anions can't form a stable compound with sodium or lithium. Size of anion is important with respect to cation size for making a stable compound. Now, in alkali metals, Lithium make lithium nitrate exactly for the same reason. Three negatively charged electrons are distributed over a small nitrogen atom, making the N3 negative anion, which form a stable compound with strongly polarizing lithium ions. Only this is a compound that makes a lithium nitrate because of high polarizing power of lithium. Now let's talk about another property of alkali metals in liquid ammonia solution. What we'll get when you put alkali metal in liquid ammonia, we get deep blue colored solution. Let's put a sodium here. What we get? A very deep colored solution because of ammoniated electrons. What happens? We know ammonia got sodium got very low ionization enthalpy. Because of that, sodium can easily supply electrons. These electrons interact with the ammonia molecules to make ammoniated electrons as well as the sodium ammonia complex that is positively charged. And these complexes are responsible for giving a blue color to solution. These ammoniated electrons responsible for giving a blue color to solution. And the presence of these complexes, ammoniated electrons as well as sodium ammonia complex being positively charged, make the solution conduct electrically conductive. Next is formation of hydrides with alkali metals. Upon heating, alkali metals form hydrides. Here is hydrogen and alkali metal. We heat it. What we get is hydride of alkali. And all alkali metals on heating at 673 Kelvin or 400 degrees Celsius make these hydrides, while lithium interact with hydrogen at very high temperature. Nearly, you can see here, it is 800 degrees Celsius to make hydride. Alkali metals. Another important chemical property is salts of oxo-acids. These are either carbonic acid, sulfuric acid, nitric acid. These are the acids that make oxo salts. Important property why we call it oxo acids because of presence of OH group, and this OH group is ionizes to give us proton to make a solution acidic. Here again OH, OH. This is dibasic, and this is unibasic acids. So first oxoacid compound is lithium carbonate. Let's discuss about it. Lithium add two lithium atoms or lithium ions interact with the carbonate group to make a lithium carbonate. Now, high polarizing capacity of lithium cations distort electron density of carbonate. So, what happens? We know compared to carbonate, where the two electrons of the two electron density spread over this whole molecule, it it distorts the electron density or destabilizes here, you see. Compared to this one, lithium oxide is more stable, having a 2 unit of negative charge over a single oxygen atom. Thus, lithium carbonate is not that stable. If we heat it, we get stable lithium oxide as well as CO2 decomposed out of this lithium carbonate. So for stable lithium oxide formation is explains that just decomposition. Next is sodium carbonate. You see, the large size sodium atoms relatively stabilizes this carbonate anion and making sodium carbonate. So further we see the stability of these compounds increases from sodium carbonate to cesium carbonate. Because of increase in electropositive effect of these alkali metal elements, or we can see the increase in charge to radiate ratio from lithium to cesium. Again, the same reason we saw earlier, decomposition of lithium carbonate. For the same reason, lithium nitrate decomposes on heating to make lithium oxide and nitrogen dioxide evolves with the evolution of nitrogen dioxide and oxygen. The reason is same, the high polarizing power of lithium. That's what we got. Lithium nitrate decomposes to LO2, L2O and nitrogen dioxide plus oxygen. Similarly, sodium nitrate, it reduces its size because this is too big a molecule. Nitrogen, this nitrate molecule decomposes to give us nitrite and oxygen. That's what we got. Next is solubility of alkali carbonates and halides. First, we know all these are solids. They form lithium fluoride, lithium chloride, lithium bromide, lithium iodide. These solids are held in crystal structure, and the energy released in that process is called lattice enthalpy. The energy released for the formation of lattice structure from its cations and anions is called lattice enthalpy. It is a 3D arrangement of these ions. When you put water into it, it should dissolve. But there is a condition for the dissolution. The condition is called hydration energy, which is energy released after hydrolyzation of ions. For a solubility, lattice enthalpy has to be smaller than hydration enthalpy. Means the hydration of individual ions should compensate for the breaking of lattice enthalpy. So, what we see? What to expect? You see, lithium, we know, lithium cation having a very strongly polarizing character, and fluoride, again, small size anion. So, it is fairly stable. We already saw it. This high polarizing capacity stabilizes the negative, uninegative charge over fluoride anion. From here, the size of anion keep on increasing. If you remember Fajan's rules, smaller the size of cation, larger the size of anion, higher will be the covalent character of that molecule. For the same reason, you see, because of the highly covalent character relative to the lithium fluoride, this lithium iodide structure is easy to break, so its lattice enthalpy will be smaller compared to lithium fluoride, and that's why the solubility increases from fluoride to iodide. Next is again sodium fluoride having the same reason. Solubility increases from fluoride to iodide. But for case of cesium, here the size of cation is considerably large, and here fluoride is considerably smaller in size. While here, both cation and anions of approximately similar size. That's why cesium iodide is better stabilized compared to cesium fluoride. So the hydration energy here compensates for the lattice enthalpy. That is the reason cesium fluoride having a little better solubility than cesium iodide, whose hydration energy is considerably smaller. Hydration enthalpy of cesium fluoride makes it better or more soluble compound compared to cesium iodide. So here we see a reversal in the solubilities from lithium to cesium. Lithium having a fluoride as a highly soluble, lithium iodide as a highly soluble compound compared to lithium fluoride, but in cesium fluoride is highly soluble compared to cesium iodide. Hydration energy is smaller compared to alkali carbonate solubilities, lithium carbonate, sodium carbonate, calcium carbonate. Lattice energy reduces more than the hydration energy down the group. So solubility increases from sodium carbonate to cesium carbonate, because we know hydration energy only have to be greater. Down the group, both the hydrogen energy as well as that lattice enthalpy reduces, but the reduction in lattice enthalpy is more than the reduction in hydration enthalpy. So hydration enthalpy will be more than the lattice enthalpy in case of cesium carbonate, making it most soluble compound.